All right, so in this video, we're going to take a look at some calculation examples from both potential energy and electric potential. These are examples that are actually in the lecture slides, but were not in the older recorded videos. So here in this first one, we are taking a look at the electric potential energy of two protons separated by a typical proton-proton intranuclear distance. So if we picture the atom, you're going to have kind of the nucleus of the atom, and of course you're going to have electrons on the outsides in that electron cloud, not going around in orbits, but moving around randomly, but sticking at kind of average distances. And then inside of our nucleus, we have our neutrons and our protons. In these smaller atoms, we actually have equal numbers of protons and neutrons, but as the atoms get larger, basically this repulsion between those positive charges gets larger and larger. And so you need more neutrons to act as buffers. So that's why you get into those really, really large atoms. You get the isotopes with different numbers of neutrons in them with different levels of stability. So in this case, we're going to be looking at kind of a typical proton-proton intranuclear distance. Now, the neutrons themselves have no charges, and we're assuming that our electrons are really far away, so we don't have to worry about them. So we're just looking at kind of a typical atom with two protons. So if you're ignoring everything else. So this would be, say, a helium atom that has that core right there. So if I picture what's going on, I have these two protons, and they're separated by some sort of distance. I'm going to call it r, and that's going to be 2 times 10 to the negative 15th meters. These are going to be equally charged protons, of course, and they're going to have charges equal to 1.6 times 10 to the negative 19th coulombs. Now, what we're doing here is we're looking at the potential energy of 2 point charges. So the equation that relates those is that our electric potential energy of point charges is K Q1 Q2 over R. So in this equation, you do need to include the signs of the charges, because remember, you get different options depending on whether it's repulsive or attractive. So the potential energy is one of these two functions right here. Just kind of going back and refreshing our brains. So you can have positive potential energies and you can have negative potential energies. This one right here is the one that actually looks like universal gravitational potential energy when you were looking at like planets and things. So this is always negative, and this represents attraction. Your potential energies are always negative when you have attractive forces, and your potential energies are always positive when you have repulsive forces. So because we have two protons, that's going to be repulsion, so our answer should come out positive. So in this case, all we really have to do is just plug in the values because we have them. So our electric potential energy is going to be K, which is 8.99 times 10 to the 9th Newton meter squared per coulomb squared. And then we're going to have that 1.6 times 10 to the negative 19 coulombs, but that is going to be squared, because these guys are the same, so Q1 times Q2 is just going to be Q squared. And that is going to be over R. Be careful, this is over R, not over R squared. The electric force is over R squared. So then our R is just going to be 2 times 10 to the negative 15th meters. And if you plug that into your calculator, you should get an electric potential energy that is equal to a positive 1.15 times 10 to the negative 13 joules. All right, so in this example, we're actually looking at the electric potential energy of a hydrogen atom. So your hydrogen atom is made out of a single proton and a single electron. So the proton is going to have a charge of positive Q. Our electron has the same charge but negative, separated by that distance d, which is the average location of that first energy level in that Bohr model of the atom. So our electric potential energy is still going to be K Q1 Q2 over R. We need to make sure we include the sign. So Q1 is going to be positive Q, Q2 is going to be negative Q. I'm going to use D for that separation distance. And that electric potential energy is going to be negative kq squared over d. And that negative is really important because this is potential energy that is attractive, related to an attractive force. So going back to our previous example, we are going to be down here on this side where we are at some position D, which is going to be that the electron-proton distance in this case. And we are going to have negative values of potential energy because it's attractive. If I was to try and move this electron further away, that would actually result in a gain in energy. So if an electron gains energy, it actually has to move out to a higher distance. When you start talking about some of your chemistry and stuff like that, location of that electron and gaining energy and jumping energy levels, that's happening because of this potential energy function. So if we were to then plug in numbers, I would get my K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Q is going to be 1.6 times 10 to the negative 19th coulombs over my separation distance of 5.29 times 10 to the negative 11th meters. So when you plug in, that potential energy is negative 4.36 times 10 to the negative 18th joules. So compared to that previous example, we have negative potential energy, and then also our potential energy is smaller in magnitude than with those protons, because those protons are actually closer together in the atom. So when you think about it, our proton was here. The separation distance within the proton nucleus is going to be a lot smaller together because the nucleus is very compact. The electron cloud is very spread out. And so you end up with the proton-proton repulsive force as being a larger magnitude than the negative attractive force, creating potential energy for the electron cloud in the nucleus. All right, now this example is a little more complicated because we're not just using a single equations for potential energy, because we're actually looking at the protons that are released from rest, and we want to know what maximum speed that they can reach. So if I picture that we're starting off with these two protons, starting here at some distance d from each other. So that's going to be Q and that's going to be Q. What's going to happen is that we are getting repulsive forces, and those repulsive forces are going to be acting in opposite directions, causing each one of these charges to move away from each other. So that's going to increase the overall distance from them. So I don't actually care what those distances are. I could figure this out, but it would be difficult. But the problem is that electric force is dependent on distance. So the further apart they are, the smaller the force, which means the acceleration is non-constant. So if I did want to solve this with kinematics, I couldn't use kinematic equations because my acceleration would be non-constant. So it's a lot easier to solve these types of problems with conservative forces when we're looking at speeds and energies using a conservation of energy standpoint. So essentially here at position 1, I'm going to call this their initial position 1, state 1. They are going to be at a separation distance of d. And when they reach their maximum speed, they're going to reach their maximum speed whenever their potential energy is at a minimum. So if we take a look, we're starting off on this potential energy graph right here at some position. Because this is an inverse relationship, the further apart that they go, so the further those particles are away from each other, the smaller and smaller that energy is going to be. So where's that energy going? That potential energy is being converted into kinetic energy. So my potential energy can never actually reach zero, no matter how far apart these are. So we're starting here at R equals D. Okay, that's their initial separation distance, okay, is D. And then we need to go till when their separation distance R is infinity. So we want to go towards infinity. And what we're going to assume is that U of R equals infinity is going to be 0. And that is when our kinetic energy is going to be at a max. So essentially at position 1, I have no kinetic energy because they are released from rest. So if I think about like U1 plus K1 is equal to U2 plus K2, I'm assuming that my kinetic energy at the start, all right, that my kinetic energy at the start is 0. And I'm going to assume that at the end, my potential energy is 0 because all of that energy has been converted. So the potential energy at the start has to equal my kinetic energy at the end. So my potential energy at the start is going to be K Q1 Q2 over R, and that's going to equal 1/2 mv squared. But here's the thing, they're both moving. So this is basically 1/2 of my total mass squared times the speed squared. Now I'm assuming because they're both protons, they have the same mass, so they're going to have the same speed. So if you want to picture like this is K1 or K2 of Q1 plus K2 of Q2. And because they have the same mass, we can just simplify that into 1/2 m total v squared. I don't need two separate potential energies over here on the left because that is the potential energy of my system. If I had one charge, there would be no potential energy. So I just have to be careful that I am looking at that kinetic energy of my whole system that is all going to be moving at a speed of v. So that m total is going to be 2 times m. So K Q1 Q2 over R is equal to 1/2 2 times the mass of a proton, v squared. So those halves are going to cancel with the 2. So this gives me that K, and these Q's are the same, right? So that's just Q and Q. So that's just Q. That's just Q. So I can do K Q squared over R, and this R is actually D, right? Because that is our starting value of R. KQ squared over D is equal to mass of the proton times V squared. So V squared is going to be KQ squared over D times mass of a proton. And then I can take that square root. So my speed is going to be the square root of K Q squared over D mass of the proton. If I wanted to, I can pull that Q out. So simplified down would be Q square root of K over D mass of the proton. So I'm going to pause here a second, kind of clear off some space. So of course at this point, we always show the substitution in of our values. So our speed is going to be Q, which is 1.6 times 10 to the negative 19th coulombs, times the square root of K, which is 8.99, times 10 to the 9th Newton meter squared per coulomb squared. My distance is 2 times 10 to the negative 10th meters. And the mass of my proton, which is on the formula sheet, is 1.67 times 10 to the negative 27th kilograms. And then I could plug that in, and I get a speed of 26,249.8 according to my calculator. That's meters per second. So using, approximately 2 to 4 sig figs, let's go with 3. That's going to give me 2.62 times 10 to the 4th meters per second. All right, so in this problem, we're actually looking at the potential. So this is our electric potential V due to the proton in the hydrogen atom at the electron's position. So recall that electric potential energy is dependent on the interaction between two charged particles. So you would need both the proton and the electron to be present. Now there's actually a couple different ways to go about doing this problem. The first one, we actually did find this answer in electric potential energy 2 problems ago. So we could use the equation that our electric potential energy is equal to Q0 times V, or the definition that V is equal to the electric potential energy divided by Q0. I think those are the same equation. I don't remember exactly which one's on the formula sheet. But we could use that relationship because we had actually already found our electric potential energy. And then Q0 would be the electron. So this one would actually be Q0, and then we're treating our proton as our source charge Q. So we could actually do that version and get the answer. But in this case, I'm going to assume that I haven't already solved for that electric potential energy and that it's unknown. In that case, I can still use this relationship right here. And I know that my potential is going to be based on my potential energy of 2 charged particles, which would be K, Q of my source, Q0 over the separation distance R divided by Q0. And what would happen, like in the lecture, is Q0 cancels out, so we get V is equal to KQ over R. Now this formula is on your formula sheet. I just wanted to remind you where it came from and the fact that this formula only works for a point source charge. So for our point source there. So what we're doing in this case is we're actually picturing that we have eliminated Q0 from the problem. So all I want to know now is what is the potential at the point in space where that electron would be. So this is dependent only on my source charge. Okay, that's what makes electric potential different from electric potential energies, because it's dependent only on the source. Kind of like the electric field is dependent only on the source and is independent of the test charge put in place. So comparing these once again to the fact that like our electric field is equal to our electric force over Q0. So these are like very similar relationships. So not needed to solve the problem, but understanding where the equations come from. Because this is one of the big mistakes that we make is we use equations that aren't necessarily valid for every situation. So the equation we're about to use is only for the point source. So when we do that, our potential is going to be KQ over R. So RR is going to be this distance D between them. Q is going to be the charge, the elementary charge right there. So I could rewrite this as KE over D if I wanted to, using the symbols that are actually in the diagram provided for us. So K is going to be 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, times 1.6 times 10 to the negative 19th coulombs for E, divided by my separation D, distance D, which is 5.29 times 10 to the negative 11th meters, which is the average location of an electron in a hydrogen atom. And when you plug all of that in, you should get a value that is approximately 27.2 volts. Sorry, getting a little close to the bottom there. So about 27.2 volts. So we have that wonderful business there. All right, in this next example problem, we have 2 source charges, Q1 and Q2. Q1 is located at the origin, and that is going to be a 1 microcoulomb charge. Q2 is 4 meters along the x-axis, so that is a negative 4 microcoulomb charge. And what we want to do is we want to calculate the electric potential at point P 3 meters along the positive y-axis. So right here. So once again, there's no test charge at point P. We're just looking at that at electric potential. So what's wonderful about working these problems in potential rather than with electric fields or electric forces is potential is scalar. So there are no vectors to draw. There are no x and y components. We just have to make sure that we are using the correct variables in the correct locations. So my potential is going to be the sum of the potential due to Q1 and the potential due to Q2. So my potential due to Q1, this is just our point charge, so that's going to be K Q1 over R1. And V2 is going to be K Q2 over R2. Now, why these aren't vectors, we do have to remember that sign does matter. We can have positive and negative potentials, so we do need to make sure that we're paying attention to the signs as we sub in. Now, R1 is just going to be this 3 meter distance, so that's going to be R1. And then R2 is going to be the distance here, which is actually the hypotenuse of this triangle. And this is a 3, 4, 5 triangle. So R2 is just going to be 5 meters. So with that, I actually have everything that I need. So K is going to be 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Q1 is going to be, this is in microcoulombs. I have to convert those to coulombs. So that is going to be 1 times 10 to the negative 6 coulombs over the distance of 3 meters squared. And then I need to add our value for the second one. So that's going to be 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times a negative 4 times 10 to the negative 6 coulombs. Remember that micro is times 10 to the negative 6, nano is times 10 to the negative 9th, and that one's going to be over, 5 meters. I got a square there. I do that all the time. Over 5 meters. I'm so used to working with like electric fields that I always make the mistake of squaring the denominator. So I apologize for that. There's no squares on the distances in this case. So then when you go through and plug those in, so when I plug all of that in, I get a value of negative 4,195 volts. So that number is negative because I've increased my denominator by less than 2 times. So I didn't quite double the denominator, but I did increase the numerator by 4 times with the negative, so that negative term wins out. So our potential does come out negative. And these are pretty large voltage values because they are over a very large distance. And also we're looking at the microcoulombs instead of like nanocoulombs. So those are pretty decent charges. All right, so this one is going to kind of pull in from our previous answer. So we found the potential at point P, but now we want to know, okay, what amount of work is going to be needed to bring a charge from basically infinity into that point. So that's that 3 microcoulomb charge. Whoop, there it is. So there's now going to be Q3 at that location. So work is going to have to be done. That external work would be equal to our change in energy, which would be the sum of the change in kinetic and the change in potential energy, because we're actually going to have to do work to move it into place. But we're going to assume that we're starting it at rest and ending it at rest, so we're not going to have any change in kinetic energy. So in this case, our external work is being used to cause a change in potential energy. So using our relationship that our potential is defined as the ratio of our electric potential energy to our test charge, we can rearrange that and define our change in potential as equaling my change in potential energy over Q0. In this case, Q0 is my test charge Q3, and rearranging to solve for my potential energy. So this is a nice, easy way to do this problem because I can just use the information that I had before. So my change in potential is going to be my ending potential minus my starting potential. Well, I'm going to assume that my potential energy is 0 when I'm infinitely far away. And that is the assumption that is being made with the equation V is equal to KQ over R, because if I was to plug in infinity for R, I would get a constant over infinity, which goes to 0. So we're going to assume that that potential in infinity is 0. So I get that my external work is going to be that 3 times 10 to the negative 6. That's our coulombs. That's our microcoulombs, converting our charge to microcoulombs to coulombs. And then this is our volts. That's our answer from the previous one. We got, I think in our calculation, we said that V was negative 4,195. So rounding that one to 2 sig figs, they're getting that our volts is negative 4.2 times 10 to the third volts. Okay, so then plugging in those values, we find that the amount of external work that has to be done is negative. So why is that negative? Well, if you think about it, we have a positive test charge, but our potential at this point was actually negative. So what that means is essentially the negative charge is more strongly influencing the space than the positive charge. So that positive charge actually is attracted to point P because of that electric field. And that electric field is actually going to be drawing in that positive charge at that point. And causing a negative amount of potential energy. So because it's an attractive force. So actually, if I wanted to move this charge from infinitely far away at rest to being here at rest, I would have to use a force that is basically holding back Q3. That's what that negative work is, because basically that charge wants to accelerate. If I was to release it from rest, it's going to accelerate in towards point P from wherever it came from, because it's going to be attracted to the field at that point. So that's what that negative work means. That work means that basically my external force has to hold back that charge to prevent it from accelerating.